Welcome to this part of the topic, which is of course the last part. We are going to take a look at transformers. We have looked at simple phenomenon of magnetism. We also looked at electromagnetic effect. In the previous video, we looked at AC generators and now transformer. What is a transformer? A transformer is basically a device used to change the voltage of an AC supply. So here is a situation. At Kariba, the ZESCO generates a high voltage of AC. That high voltage is the one that is meant to supply a bigger portion of Zambia. So how is it possible that we can charge our phones that don't need that much high voltage? It is all because of a transformer. The transformer will get that high voltage and it's going to reduce it. The job of a transformer is to change the voltage level from a high to a low or from a low to a high voltage. That's what transformers do. So a transformer basically consists of a primary coil, a secondary coil, and a soft iron core. So remember when we talked about the solenoid, which was made of a coil around an iron core. It's the same concept, but here we're going to have two types of coils, a primary coil and a secondary coil. So a transformer looks like this. So here we're going to have AC supply, something that produces AC. It can be a simple AC generator or anything. So that AC supply is going to be connected to a soft iron core. A soft iron core. So the way it's going to be connected is we're going to have windings around the soft iron core. So these windings are what makes up the primary coil. Then on the other hand, we're going to have another soft iron core, which is going, of course, to have other windings, and the windings from here are going to be connected to what's going to use that electricity, which of course we usually call it generally as the load. So that is the general term that we refer to what uses electricity. So with all these parts, how does a transformer works? Remember, the job of a transformer is to get this high voltage and to reduce it, or to get a small voltage and to increase it. So to understand the science of a transformer, it all goes back to the science of electromagnetic induction, where current is induced in a wire if it is cutting or moving across a magnetic field. Okay, so remember when we were studying AC generators, had introduced the concept of a magnet and a wire. I said there are two ways in which the current can be induced. First is where the magnet is stationary, which implies that the magnetic field is also stationary, and a wire is moving. So as the wire is moving, it will be cutting across the magnetic field and current is going to be induced. The other situation is where the wire is stationary and the magnet is moving. A moving magnet implies a moving magnetic field. That moving magnetic field is going to be cut by the wire, which is stationary, and therefore current is going to be induced in the wire. So in AC generators, it was all about the first scenario, where the wire is moving, cutting across the field. In this transformer, we don't have actual movements, but we're going to have a movement that comes from a changing magnetic field. Not the changing magnet, but a changing magnetic field. So how is it that we can have a magnetic field that is changing? Well, the magnet itself does not change. We're going to understand that soon. So AC is a current that changes direction many times. Okay, when we are talking about the solenoid, when we are talking about how electromagnets are made by winding a wire around a soft iron core and then connecting that wire to a DC supply, and then we could use Fleming's right hand rule to tell where North Pole is and where South Pole is. So that concept is the same here, but here we don't use DC, we use AC. So why AC? So AC changes direction many times, like I said. So in the first scenario, let's assume the current is moving like this. When current is moving like this, if you use Fleming's right hand rule, maybe you can find that your north is going to be somewhere here and your south is going to be somewhere here. Okay, so but AC changes direction so many times in a second. So as the current is moving here, then it changes, starts moving here. It means your north is going to be here and your south is going to be here. So as these changes keeps on happening, then also the poles are going to be changing. So AC, the changes happen so fast in a second. In Zambia, we use 60 Hz, which means that the changes happen 60 times in a second. Therefore, this magnet is going to be changing poles 60 times in a second. So if the poles are changing, what happens to the magnetic field? So in the first situation, let's say north is here and south here, the direction of the magnetic field will be moving the magnetic field is going to have one direction, and when the poles reverse, then the direction of the magnetic field is going to reverse also. So as the poles are changing, the direction of the magnetic field is also changing. The changing of the direction of the magnetic field means the magnetic field itself is changing. So that changing magnetic field, if it's reaching here, it will have the same effect as a magnet that is moving, because a magnet that is moving implies a magnetic field that is changing. So even a magnet that keeps on changing poles, you can view it as a magnet that is being rotated, like up down up down up down, just like that. So the magnetic field is going to be changing. The changing magnetic field, if it is passing through the wire, will have the same effect as a magnet that is moving towards a stationary wire, and current is going to be induced. Okay, in summary, the changing AC produces a changing magnet. A changing magnet means a changing magnetic field. A changing magnetic field means current is going to be induced here. Even the current itself that is being induced is going to be a changing current, which means it's going to be AC also. So the frequency of this AC, or how fast this AC changes in a second, is going to be the same as this AC, which is going to be here. So now the only thing that can be different is the voltage or the current of the AC here. So what determines that voltage or current is the number of the turns here and here. The turns, I'm talking about these ones, the winding. So we refer to the winding as turns. So here we have 1, 2, 3, 4 turns. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9 turns. So what determines the value of the voltage or current that's going to be produced in the secondary coil are the number of turns here and the number of turns here, and of course the value of the voltage here. So the beauty about transformers is there's no physical contact between the supply of AC and the user of AC, but the contact is through the changing magnetic field, which induces the current. So this is the equation we use to determine the value of the voltage in the secondary coil. So the VP here is primary voltage, then VS is secondary voltage, all measured in volts. NS is the number of primary turns, and NP is number of primary turns, and NS is number of secondary turns. Okay, so if you have been given the voltage at the supply and you want to find the voltage that's going to be in the secondary coil, if you know the number of turns in the secondary coil and the number of turns in the primary coil, then you can use this equation to find the voltage in the secondary coil. So for an ideal transformer, which basically means a transformer with 100% efficiency. Remember, when we were talking about simple machines, we talked about efficiency, and most machines, actually all machines, are not efficient, or they don't have 100% efficient because of energy or heat losses. So for an ideal transformer, or a transformer with negligible losses, then there is an equation that connects the primary voltage, secondary voltage, primary current, and secondary current. And the equation is this: secondary voltage over primary voltage is equal to secondary current over primary. Next, we look at types of transformers. So there are basically two types of transformers. The first are called step-up transformers. So step-up transformers will get a small voltage and increase it to a higher value. So in this type of transformers, the voltage in the secondary coil is always higher than the voltage in the primary coil. The number of turns in the secondary coil is always greater than the number of turns in the primary coil. So this is an example of a step-up transformer. The number of turns are less than the number of turns here. The voltage here is less than the voltage here. The second type of transformer are step-down transformers. So these do the opposite, a higher value to a lower value. So in these ones, the voltage in the secondary coil is lower than the voltage in the primary coil. The number of turns in the secondary coil are fewer than the number of turns in the primary coil. So an example is this. So at supply of 240 volts, then at the load of 100 volts, then the number of turns here are too many as compared to the number of turns in the secondary. Let's take a look at an example. A step-up transformer increases the voltage of AC supply from 110 volts to 220 volts. The primary coil dissipates the power of 1.1 kilowatt, and the efficiency of the transformer is 100%. This means that we can use that equation for current and voltage at some point. If the turns in the primary have 400, how many turns are in the secondary? So they have given us the primary voltage, the secondary voltage. They have given us the primary turns, they want the secondary turns. We know the equation to use. The second question is how much current flows in each coil. So in the primary coil, of course, we cannot, since the transformer is 100%, so we can use that relation between primary voltage, secondary voltage, and primary current and secondary current. Now the issue is how do we determine the primary current, because they have said how much current flows in each coil, meaning the primary coil and the secondary coil. So we haven't been given any current, so there must be a way to calculate the current in the primary or secondary. Then we use that, we use the current that we're going to get, we use the equation for the transformer to get the other current. If you don't get what I've said here, don't worry, you will. So the first question is simple. What have we been given? So I've been given the primary voltage, the secondary voltage, the primary turns. We're looking for the secondary turns, so we can apply our formula. Primary voltage over secondary voltage equals primary turns over secondary turns. So primary voltage, secondary voltage over primary voltage. So secondary voltage is 220 volts. Then primary voltage is 110, which is equal to number of secondary turns, which we're looking for, over number of primary turns, 400. So when you solve this, when you divide here 220 divided by 110, when you do cross multiply 110 times ns, you're going to have 110 ns. Then 220 times 400, you're going to have 88,000. Then you can divide both sides by 110, and you're going to have 800 turns. So the next question now, how much current flows in each coil? We know the number of turns in the primary and secondary coil. We know the voltage in the primary and secondary. But about current, we can't use that formula if we haven't been given any current. We have to be given either the primary current or the secondary current. So we must figure a way to calculate one of the currents, either primary or secondary. So when we go to our question, it says the primary coil dissipates the power of 1.1 kilowatts. They have given us the power 1.1 kilowatts. okay, in the primary. Also primary, they have given us the voltage 110. We can use the formula for power, the formula that connects power, voltage, and current. So we can say the voltage in the primary is 110, but power is 1.1 kilowatts, which if we convert, it's going to be 1100 watts. So power is going to be voltage times current, which is supposed to be primary current here. You forgive me for this. So what's the voltage, what's the power? So the power is 1100, the voltage is 110 volts times secondary primary current, supposed to be primary current. We're talking about, we're analyzing the primary coil here. So we can divide both sides by 110. When you do that, we're going to get 10 amps. Next, we this is the current in the primary coil. So to get the current in the secondary coil, we used our transformer equation. So we can plug in 220 volts, which is the secondary voltage, over 110 volts, which is the primary voltage. Then the secondary current we don't know, but the primary current is 10 amps. So when we try to divide this side, we're going to have 220 divided by 110 is going to be 2. Or you can do cross multiplying, whichever you're going to do, you're going to arrive at the same answer. So you can do cross multiplying here again. You're going to have 2 times 10 amps, going to give you 20 amps. So this is how to get the secondary current. This marks the end of magnetism. Happy solving.